Hi! In this video we'll be computing some eigenvalues and eigenvectors, and these are exactly the steps that we will take, and we will do it with this example matrix here. So let's just get right into it and start with the first step. Namely, we want to find the characteristic polynomial. So how is that defined again? So we look at the determinant, not of this matrix, but of this matrix minus, well, some constant, which is lambda, times the identity matrix. So the matrix with only ones on the diagonal. So what is this matrix in our case? So we subtract lambda on the diagonal. So the first term becomes 1 minus lambda. Then these two don't change, so we have 2 and 0. Then we have 2, 1 minus lambda again, and a 0. And then finally we have 0, 2, and again 1 minus lambda. Alright, so now we want to compute the determinant here. And I hope that you remember that to compute a determinant, it's always good to find some row or column where we have a lot of zeros. So in our case, this column has 2 zeros, so that means less work for us. So we will look at this column, and then if you remember, we look at this chessboard, so we have a plus, minus, plus, minus, plus. So this is the only term that we have to look at, so we get 1 minus lambda with a plus because of the chessboard, so just 1 minus lambda, times the determinant of what? Well, we get rid of this row and column here, and we look at what is left. So we have 1 minus lambda, 2, 2, and 1 minus lambda. And we don't have any other terms because these two are 0, so that's nice. So the determinant of this thing is easy to compute because it's just a 2 by 2. So we get 1 minus lambda times 1 minus lambda, so 1 minus lambda squared, minus 2 times 2, so minus 4. I forgot a bracket here. All right, and now we could get rid of these brackets, but we actually don't really want to because of the next step that we will take. So in step 2, we want to find the roots of this polynomial. So what we will do in step 2, we will say that this should be equal to 0. And now you see why we don't want to get rid of the brackets, because the brackets actually make it easier for us to find a solution here. Well, not just a solution, we want all solutions specifically. So when is this 0? Well, this first thing can be 0, so this gives, so 1 minus lambda is equal to 0, or this second part should be equal to 0, so 1 minus lambda squared minus 4 equals 0. Well, the first one is easy, so lambda equals 1. And then the second one, if we get the 4 to the right, we get 1 minus lambda squared equals 2. And this again splits into 2 branches, so we get 1 minus lambda is equal to, oh, sorry, this should be a 4. Let me correct that. Is equal to 2, or it can also be minus 2. So what are then our final solutions? So we had lambda is equal to 1, or here we get lambda is equal to minus 1, or lambda is equal to 3. So these are our eigenvalues. So we have already solved the first part of our problem. And now for each of these eigenvalues, we use this equation to find the corresponding eigenvectors. So let's just start with this. Lambda is 1. So we need this matrix over here. So what does this matrix look like? Well, it's just this matrix with lambda is 1 filled in. So all of the diagonal elements become 0. And then we had a 2 here, a 2 here, zeros here, and a 0 and a 2 here. All right, then this times some vector v, so x, y, z, should be equal to the 0 vector. So what we see here is that these rows are not actually independent. In this example, even the first row and the third row are exactly the same. And that actually makes sense because we know that our rows are dependent if this determinant is equal to 0. And we choose lambda such that the determinant is equal to 0. So that means that there's not just one solution here, but we have many solutions. And all of these solutions are eigenvectors. But we always first try to find one simple solution. So what do we know from these equations? So the first equation tells us that 2y is equal to 0. The second one says 2 times x is equal to 0. And the third one is just the same as the first one. So we know that x and y have to be 0. So we get as eigenvectors, we get x is equal to 0, y is equal to 0, and for z we can choose anything. We have no restrictions. So let's just choose the easiest thing that is non-zero, and that is 1. So this is one particular eigenvector, but it's not all of them. To get all of the eigenvectors, we should multiply by some constant. So let's say c. And c is, it doesn't fit behind here, c is some real number. So now, these vectors from all of the eigenvectors in this specific case. So let's do one other example. So let's look at lambda is equal to -1. We get a different matrix. So on the diagonal we get 1 minus -1. So we get 2 on the diagonal 3 times. Just coincidental because these are the same. This is not generally the case. Then we still had 2's here. We had a 0, a 2, and 2 zeros here. Times x, y, z should be the 0 vector. Again, we have 2 rows that are the same, but we already determined that that was correct. So, okay, so what equations do we find here? The first one tells us that 2x plus 2y is equal to 0. And the second one is the same. And the third one says that 2y plus 2z is equal to 0. Now let's first write these equations. This is not a necessary step, but it's maybe a bit easier for you to see then. If we write this in some way that we have some relation between x and y, then we can divide the first equation by 2 and move this y to the right. So x is minus y. And the second one we have y is minus z. So now we need to find the eigenvectors. That correspond to these equations. So before we had some values that should be 0. Well, we don't have anything like this time. So let's just start with putting the first value, so the value for x, at 1. we just choose any value for x. And what should then be y? So if we choose x as 1, then y should be actually minus x. So y should be minus 1. And then from the second equation, if y is minus 1, then z should be equal to 1 again. So this way, so by setting one of the variables, we find values for the other ones. And again, this is not a general solution, but if we put a constant in front here, so some constant that is a real number, then we find all of the solutions to these equations. All right, so we still have lambda is 3 left, but it doesn't really fit on the board anymore, so you can do those computations yourself in exactly the same way as we did it here. So I hope this gives you a clear plan of how to compute eigenvalues and eigenvectors, and that you can do it for any matrix now.